The project we have undertaken is to design a protective berm and actuation pond around Thomond.
The proposed location for the actuation pond and berm is shown in red.
Shown here is a close-up of the site for the actuation pond. The initial step in our project was to conduct a desk study. This was used to obtain any information already available about the site. Information such as ordnance survey maps were found in the library. By using the internet, we also found the water table level and the details of environmental impact reports that were conducted in the vicinity. Information was also gained from planning applications for previous developments in the area. A site walkover was then undertaken to assess access, gain a better understanding of the scale of the site, and confirm findings from the desk study. A trial pit was dug in the location shown. From this trial pit we could see there was 4 distinct strata. The first layer was topsoil fill that extended to a depth of 550 millimeters. The second layer was the original topsoil that extended from 550 millimeters to 1100 millimeters. The third layer was a 100 millimeter layer of peat. The fourth layer was a layer of grey silt that extended from 1200 millimeters to the bottom of the trial pit at 2000 millimeters. At 1300 millimeters we encountered perched water. An intact samples and in situ shear vein test was carried out. From the excavation, samples of each strata were taken for analysis. Collaboration with other groups allowed us to obtain further soil samples that were below the depth of our trial pit. These samples were oven dried for a week between laboratory sessions. They were then broken down to their individual particles as shown here. It was necessary to riffle some of the samples to accurately obtain a more manageable sample size. A sieve analysis test was undertaken on each of these samples. The results were tabulated and graphed to give us a grading curve of each sample. Due to there being granules of soil apart from individual particles, inaccuracies were encountered. A proctor test was undertaken to obtain optimum moisture content and relative compaction values. This was done by filling the mould with 3 layers and compacting each layer 27 times with a 3.5 kilogram hammer. The collar was removed and the sample and mould masses were found. Samples from each mould were taken to obtain the moisture content at that compaction. The results were graphed to obtain the proctor curve for that soil sample. Possibly more tests at different moisture contents should have been carried out to give a more accurate result. A CBR test was carried out on the pink clay to find its bearing capacity, as this soil could potentially be used as a foundation for the actuation pond and berm. An initial process similar to the proctor test was carried out, except this time a 5 kilogram hammer was used and 67 blows were applied. It was then put into the CBR testing machine, which resulted in an indentation as shown. We measured the penetration of this indentation in proportion to the force creating this penetration, and graphed the results.
We then proceeded to the Attenberg limit test to find the plastic and liquid limit. The plastic limit test consisted of rolling a sample of soil into a cylinder with a 3 mm diameter. If the sample crumbled before reaching this diameter, it was too dry. If it didn't crumble when reaching this diameter, it was too wet. When it crumbled at the 3 mm diameter, this was the plastic limit, and the water content of this sample was found. However, this was an empirical test, which can often lead to inaccuracies in results. The liquid limit was found using the cone penetrometer method. This consisted of letting a metal cone penetrate under its own weight into a homogeneous sample of soil and measure its penetration. The moisture content of the sample was found. Then the test was repeated for samples of varying moisture content. The liquid limit was determined from a graph of penetration versus moisture content, where the value for moisture content corresponds with a penetration of 20 millimeters. We developed a schematic design showing a cross section through the berm. We then calculated seepage rates through the dam with a factor of safety of 2 in mind. However, we did not require to calculate the seepage underneath the berm, as we were planning to place an impermeable layer underneath the berm. The seepage slope was found to be 30 degrees, however we changed this to 26.56 degrees to allow for slope stability, as the standard berm slope is 2:1, giving an angle of 26.56 degrees. This is a standard flow net diagram for our berm. We calculated using Casagrande's method the location of the phreatic surface for our berm. This also aided us in obtaining a preliminary size for a drain, which will be required to control the seepage flow and prevent erosion and piping. We analysed the hydrostatic pressure imposed on the berm by the water and compared it to the frictional resistance of the berm. This was to ensure the berm did not slide. The design of the foundation of the berm would require further analysis to see whether base heave would be an issue. The issue of swelling soils and the negative effect this has on berm integrity was investigated. Here you can see the geometry and dimensions of the proposed berm. If upon more in-depth analysis of the flow net, it turned out that there was an excessive amount of seepage through the berm from using on-site materials, an option could be to line the base of the pond and the inside of the berm with impermeable membrane, hence preventing any unwanted seepage. The health and safety aspect of the berm was addressed. With the advantage of hindsight, we found some aspects of the project we would have done differently.